Assalamualaikum and very good afternoon. Welcome everyone to Distinguished Lecture Series number 12, brought to you live from Faculty of Engineering, University Technology, Malaysia. I am Professor Dr. Nazri Ali, hosting for this lecture series today. For your information, this Distinguished Lecture Series, we invite prominent professors around the globe to share their knowledge and exchange ideas. So it's a great pleasure for me to introduce our speaker today, Professor Dr. Harianto Rahardjo from Nanyang Technological University, Singapore. Prof. Harianto will deliver the lecture in Sustainable Urban Development today. So for those who know Professor Harianto, Prof is well-known professor in field of geotechnical engineering. He and Professor Fred Lentz already produced famous reference textbook in geotechnical engineering, Unsaturated Soil Mechanics. I'm still remember when I'm doing Ph.D. in Cardiff University, and many of my works are referred to Professor Harianto books. So I know him for many years. So we have met a few times in conference and also in workshop. And I already invite him for 2 times to become my PhD student external examiner. Without any delay, now I invite Professor Dato' IR Dr. Muhammad Rafiq bin Dato' Abdul Qadir, Dean, Faculty of Engineering UTM, for further introduction of our speaker. Prof. Rafiq, over to you.
Thank you, Nazri. Assalamualaikum and hello, welcome everyone. Welcome to our 12th UTM Engineering Distinguished Lecture Series. My name is Rafiq and I am the Dean of Engineering, University of Technology, Malaysia. Today, it is my utmost pleasure to welcome Prof. Harianto Rahardjo to our program. A bit about our presenter today. Harianto Rahardjo is a full professor since 2004 at the School of Civil and Environmental Engineering, Nanyang Technological University, Singapore. He obtained his Ph.D. and M.Sc. in Geotechnical Engineering from University of Saskatchewan, Canada, and his B.Eng degree in Civil Engineering from Bandung Institute of Technology, ITB, Indonesia. He has close to 40 years of working experience in consulting, teaching, and research in geotechnical engineering. He has served as Vice Dean, Associate Chair for Research, School of Civil and Environmental Engineering, Director of NTU-PWD Geotechnical Research Centre, Head of Division of Infrastructure Systems and Maritime Studies, Nanyang Technological University. He has published over 400 technical publications and presented his research works in over 60 keynote invited lectures in various countries. Among the prizes and awards that he received include the 2019 Korean Geotechnical Society Awards Lecture, Minister for National Development's R&D Special Mention Award in 2017, and winner of the Inaugural Asia Pacific Distinguished Lecture on Unsaturated Soils in 2015. He is the co-author of the first textbook on unsaturated soils, The Soil Mechanics for Unsaturated Soils, published in 1993, and has been translated into various languages in various countries. Other books that he co-authored include Unsaturated Soil Mechanics in Engineering Practice, published by John Wiley in 2012, and Unsaturated Soils Guidelines, Volume 1, Soil Water Characteristic Curves for Materials Classified according to the Unified Soil Classification System in 2019. So that is a brief biography of our speaker. Here now is Professor Harianto Rahardjo from Nanyang Technological University, Singapore, to talk about urban sustainable development. Prof. Rahardjo, over to you.
Very good afternoon, ladies and gentlemen. First of all, I would like to thank the University of Technology, Malaysia, for inviting me to give this lecture. And I would like to thank Professor Rafiq and Professor Nazri for their kind introductions. Let me start with my first slide. The title of my lecture is on the sustainable urban development, particularly the contributions of unsaturated soil mechanics in urban development that is sustainable. So the PDF file of the presentation slides can be downloaded from the following digital library of myself and Dr. Alfredo Satyanaga, who has been my collaborator in many research projects in this area. So first of all, we are quite familiar with slope failures due to rainfall. This is an example, one of the largest failure in Singapore due to rainfall. And particularly become important in the midst of global climate change. We realize the temperature in the world already keep on increasing. Same thing with the global mean sea level rise. And if we look in Singapore itself, the total annual rainfall also increases for this particular period, and the annual mean temperature also increases. And if we look at the intense rainfall, that is more than 70 millimeter, within 1 hour, during this period, the trend is very clear. There is an increase in the intense rainfall on the island. So certainly it has some consequences on slope stability. Now, let's look at situations in December 2006. We have heavy rainfall throughout the month, and this the third largest ever recorded rainfall in Singapore. And you can see all those red points. Those are locations of slope failures. What do we learn from here? Many of the slope failures did not coincide with the largest amount of rainfall. So there is something else that contribute to the rainfall-induced slope failures mechanism. That is soil properties, particularly the unsaturated soil properties. Again, in January 2007, we have a large number of rainfall. All those yellow points, those slope failures around the island, they do not coincide with the maximum rainfall. So not only rainfall itself is important, but the soil properties is important. Whether the soil will take that rainfall and turn it into infiltration and change the water pressures, affecting the shear strength, and as a result, affecting the stability of the slope. So those are the characteristics that need to be taken into account. Now, as a result of rainfall during that period, you can see slope instability in one of near the water reservoir here. It's very clear that environmental changes will affect slope stability. And in turn, if you have slope instability like this, the debris will go into the water reservoir. As a result, the slope instability will also affect the environment. So there is a close relationship between environment and slope stability. So what is the problem at hand in here? Many of our residual soil slopes are high, steep, and the water table is quite deep. So the loading comes from the environment in terms of rainfall, infiltration, and evaporation, transpiration. If we look carefully in here, the zone above the water table is called the unsaturated zone. The water pressure inside that unsaturated zone is negative with respect to the atmospheric pressure. And what we call that negative water pressure, reference to air pressure, is we call it as matrix suction. Matrix suction contributes to the shear strength of the soil. So during rainfall, the infiltrations is going to cause the matrix suctions to decrease. As a result, the shear strength will decrease. As a result, the factor of safety of the slope will decrease. As a result, you may have instability problem or slope failures. So the largest changes take place near the ground surface. That's why we always notice a shallow slip surface, right? Perhaps 2 or 3 meter, and throughout the slope during rainfall, or at the end of rainfall, or after rainfall, okay, depending on the characteristic of the soil. But again, it's important that we incorporate all this environmental loading in our analysis of the rainfall, intensity and characteristic, evaporation, and the transpiration. So as the background, climate change affects the flux boundary conditions, infiltration, evaporations, and transpiration. The unsaturated zone near the ground surface is a function of flux boundary condition. So this is the zone above the water table, where we call the unsaturated zone. This is the zone that comes in contact with the environment. When we talk about environmental changes, the effect of environmental changes on slope, we can't ignore this zone because this is the direct interface with the environment. So how infiltrations take place, the rate of infiltration is a function of the permeability of the unsaturated soil, and it's a function of the matrix suction. How does shear strength change from the unsaturated conditions to a saturated condition? Again, we need to take that into account. What do we do usually in practice? We assume it fully saturated. If the soil is already fully saturated, theoretically, there should not be any effect from the rainfall. But the fact is the soil is unsaturated to start with. Then there will be infiltration due to rainfall. There is a change in the shear strength, and that's the one that causes the failure. So unsaturated properties need to be considered in the assessment of slope stability. So the objective of this presentation is to illustrate the application of unsaturated soil mechanics for sustainable development in urban areas. In other words, if we want to develop the urban areas in a sustainable manner, we need to incorporate this unsaturated soil. In fact, actually, the slope problem is a natural condition, but we encounter many of the unsaturated soil in compacted soil. Behind the retaining wall, at sub base for pavement, and many areas of geotechnical construction involve compacted soil which are unsaturated. It is impossible for you to compact the soil under saturated condition. So unsaturated soil practically exists in many geotechnical constructions. That's why Professor Houston indicated in her paper that unsaturated soil mechanics should be used in routine geotechnical practice. Now, I will not go into the theories like Professor Rafik already mentions. There are 3 books that we have published with respect to the unsaturated soil mechanics. And in fact, the first one in 1993 is the first book, textbook on unsaturated soil mechanics, together with Professor Fredlund. So the scope of the presentation, I will illustrate into 3 areas. That is the development of susceptibility map in Singapore. It makes more sense if we incorporate the unsaturated soil, because if we assume the soil all fully saturated, and then you have lots of those high-risk slopes that actually they are not high risk, and as a result, lots of monitoring need to be installed, and also a slope improvement need to be carried out, and this may be an over design. However, with incorporation of unsaturated soil, and then our slope susceptibility map will become more realistic, more reasonable, and we will be able to have urban development in a sustainable manner. Now, those slopes that already have critical conditions, the factor safety close to 1, and how do we improve it using the unsaturated soil mechanics? I will introduce capillary barrier system and geobarrier system. Then those slopes that actually less than 1.5, but still considered unacceptable here in Singapore, we can do the monitoring. Okay? And the latest part, I will talk a little bit on the contribution of unsaturated soil mechanics on the tree stability. So this is the procedures that we set up in the development of slope stability map. I'm using Singapore as a case study. This can be applied to many other areas. So we use the geological map, the digital elevation model of Singapore, and properties, saturated, unsaturated. And the analysis of slope stability, we use the transient rainfall infiltration and grid-based regional slope stability, or TRGRS, developed by USGS, the United States Geological Survey. And then we evaluate the slope, whether they're within 1 to 1.5 in terms of factor safety. We consider it is below acceptable level or above 1.5. So if it is within that range of 1.1.5, then we can consider monitoring of the slope and improving the slope, okay, the event that really is close to critical value. So these are the required parameters for the development of slope stability map. The property of the soil in the unsaturated soil, so water characteristic curve, best fitting parameters, okay, using Gardner's equation, because this is trying to fit into the TRGIS model. The hydraulic diffusivity for the unsaturated permeability function, saturated permeability, effective cohesion, effective friction angle for saturated condition, and the unsaturated Phoebe angle, the increase and decrease of strength due to the suction controlled by the Phoebe angle. And other required parameters are digital elevation model, groundwater distribution, and the rainfall characteristic, different part of Singapore. And these are the software we use from USGS. So these are the locations of boreholes in Singapore. The blue one indicate the boreholes that have C prime and Phi prime only. And the red one, those are borehole that have the information respect to C prime, Phi prime, and other unsaturated soil property. So with this, we'll be able to have a spatial distribution of soil properties across the island. Now, let's touch a little bit on soil water characteristic curve. Basically, this is the relationship between water content and suction from saturated condition all the way to certain suction value. This is remain saturated. Then this point here, we call it the air entry value. That is the suction beyond which the soil becomes unsaturated. Water content decreases rapidly. So this is important, the air entry value. Of course, there's another point they call the residual suctions, beyond which if you keep on drying the soil, increasing suction, it will not change the water content that much. So we have all the equipment in the laboratory to be able to measure those soil water characteristic curve. The pressure plate test, the Tempicell can be used for suction up to 100 kilopascal, or the pressure plate to 1,500 kilopascal. The evaporation method, or the dew point potentiometer. Now, these are the characteristics of the soil water retention. Different soil type have different characteristics in retaining water. For example, for clay, it will remain saturated until quite a high suction before it starts to desaturate. But for sand, at a small suction value, at small dryness, it desaturates very quickly. Now, this has an impact on the permeability because water can only flow through the pores that are filled with water. So if, for example, for the silty clay, now the amount of water starts to decrease, then we have the permeability of the silty clay. We start with certain saturated permeability, and then at the air entry value, the permeability will decrease. The ability of the soil under unsaturated conditions to transmit water start to decrease. Now, for sand, your saturated permeability can be higher than clay, but the air entry value is low. As a result, the permeability decreases very, very fast. Okay? So these are the shear strength of unsaturated soil. The frontal plane is for saturated conditions, C prime and phi prime. And the third axis is for the suction. As suction increases, your shear strength increases, as if you have a higher cohesion. This is what we call it, the total cohesion. In the equations, this is the unsaturated soil shear strength. So the contribution from suction is in here. So if you have higher suction, you will have higher total cohesion. And as the soil becomes saturated, the suction goes to zero. Pour air equal to pour water pressure. This term goes to zero. So go back to C prime, and pour air becomes the pour water pressure. We'll go back to the classical saturated soil shear strength. And here is the modified triaxial that can be used to measure the phoebe angle of different soil. And for the spatial analysis, we are using the geostatical analysis to do the spatial analysis. The method is the ordinary kriging. Basically, is in order to estimate of properties at a particular location, we need to interpolate it using the known properties from other locations. Here is the spatial distribution of air entry value across the island, the saturated permeability, the effective cohesion, effective friction angle, phoebe angle, and these are the digital model of Singapore, the groundwater table of Singapore. And let's look, these are the slope susceptibility map of Singapore. So there are those red points to indicate the factor of safety less or equal 1.5, because 1.5 is considered as acceptable factor of safety. Now let's zoom into the NTU zone, our campus. Here is the zone, red zone, indicate the factor of safety less than 1.5. They are quite extensive. Why? Because we specially highlight in here, if we were to analyze, we create this susceptibility map, assuming that the soil is fully saturated. This is what we have. In other words, many parts of the campus are unstable. But if we have a close inspections of those slopes, natural slope, and they can stand on its own without protection. In other words, the slopes are stable because of the unsaturated condition. And if we were to follow this map, we will have to do lots of monitoring of slopes around the campus, or we have to do lots of slope improvement around the campus. And those can be unsustainable, okay, for the urban development. However, if we look, if we consider that the soils incorporating the unsaturated soil property, then we will have a more realistic susceptibility map. So a certain area, yes, they indicate factor of safety less than 1.5. Then we have a closer inspections of that slope. It's true enough that slope has been stabilized using these retaining structures in front of the slope. So it is true, if it is less than 1.5, that the slope needs some stabilization. If the slope have factor safety not too low, but still below 1.5, we can instrument the slope using all the series of sensors. Like particularly, I mentioned tensiometers to measure negative water pressure in the unsaturated zone, and the weather station to take care with respect to the rainfall and the wind speed for evaporations, rate calculation, and so on. These are all the instruments, tensiometers, right? And water content measurements and the weather stations equipment. That's the setup for the data acquisition system. And these are all the locations of slope instrumentations in Singapore that we have installed. And particularly, I'd like to bring your attention to this instrumentations area at Jalan Koko. That's a setup. These are actually tensiometers buried at 0.5 meter depth, 1 meter, 2 meter, and 2.5 meter from crest to the toe. From here, when it rains, we'll be able to get the water pressure distribution throughout the slope, okay, from crest to the toe and at different depth. And also we have the rain gauge on the slope itself, piezometer, inclinometer, and all hooked up to the data acquisition system. Let's look at this particular rainfall and period. We have for almost 2.5 hours, and these discrete points, those are the measurements from the tensiometers, right? This is the initial conditions, and this is at 3 hours. Okay, it's basically corresponding to about the end of the rainfall. And if we use the numerical method, using the input from the soil properties of the soil, saturated and unsaturated from the slope itself, and we'll have a good match between the field data and numerical analysis, showing that the theory was that the governing equation for the numerical analysis for unsaturated soil work well, and all the instrumentations that we use be able to reflect really the process that's happening in the unsaturated soil. Same thing at the row C, which is close to the toe. They have a good match between the numerical analysis and the field measuring that data. And if we calculate the factor of safety of the slope, this is the end of the rainfall, factor of safety decreases, and yet this is not the end of, this is not the lowest factor of safety. The factor of safety keep on decreasing. Okay? This is the lowest factor of safety few days after the rainfall. Then after that, it goes back up again. So it shows the characteristic of the soil. So there are some cases the soil will still, water still percolate through the soil and reaching the equilibrium conditions, right? Limiting equilibrium condition at certain time after the end of rainfall. And this may cause delay failure in some cases that we learn there's rainfall today and a few days later the slope fail. It all depends on the soil properties. And so how do we improve the soil, the slope that is in critical conditions? This is one way of doing it. We put the non-cohesive, okay, fine grain layer, for example, sand, and non-cohesive coarse grain layer that is, for example, in this case, gravel. Under unsaturated conditions, your sand will have higher permeability than gravel. As a result, water infiltrate the sand and flow along the sand layer, and then we drain it out. This is what we call the lateral diversion, and we drain it to the main drain. And so this gravel layer acts as a barrier, hydraulic barrier. So infiltration will not be able to penetrate this gravel layer, resulting in the protections of the slope underneath. Yeah, so the this is one example of a slope improvement using capillary barrier system, utilizing the unsaturated soil mechanics. Why? Like I said, this is the SWCC for example for sand, and this is for clay, the red one. And if I look at the permeability for, sorry, not clay, for gravel. So for gravel, these are the permeability of gravel, and this is the permeability of sand. And then under unsaturated conditions, yeah, your sand will have higher permeability than gravel. It is is a shift, paradigm shift in our thinking, but that's the fact in unsaturated conditions. As a result, we can have higher permeability for this layer compared to this, and this provides a barrier effect to the infiltration into the underlying soil or the slope, original slope. And this is nothing new. It's been used a long time ago by people in Korea when they constructed the royal family tombs. So you have the fine grain and the coarse grain. As a result, water will flow along the fine grain only, and then infiltration is prevented to enter this burial chamber. So this is once the old tomb that has been dissected, and you'll be able to see the fine grain and the coarse grain. We have done the model in our laboratory, 2D model and 1D model, and it shows the effectiveness of this capillary barrier. And then we constructed in several areas. So this is one example I want to bring up. A site that has lots of instability due to rainfall. And then we put the bottom layer of geocell, contain the gravel. This is the gravel. Then the top layers, we have geocell to contain the sand. And then first we have to anchor it using the J-pin. Okay, so this laying of the sand, and then after that we have this tensiometer to measure the performance of the slope covered with the CBS or capillary barrier and the slope without the capillary barrier system. This is the results showing that slope without the capillary barrier system, the water pressures tend to be positive, and then for slope with the capillary barrier system, the water pressures remain negative under the same rainfall characteristic. And throughout the year, again, slope with the capillary barrier system, the factor of safety is higher than the slope without the capillary barrier system under the same rainfall conditions for a period of from June 2010 till January 2011. Now, the aggregates are expensive. Can we try recycled material? So, and on this side, we try the use of recycled concrete aggregate. And here is factor of safety of this slope with the recycled concrete aggregate remain high. The original slope, the factor of safety is affected by rainfall. The recycled material have been found to perform as good as the natural aggregate like gravel or sand. So these are constructions on one side using capillary barrier system. Then how about if we want to have a basement, free, wall-free, multi-level basement car park? There's no wall in here, so we need to protect that slope. Can we use a barrier system in here? In other words, we want to make sure that the slope here is stable. There's no water infiltrations into this slope. Yes, we construct, we call it the geo barrier system. There is a retaining structures consisting of fine grain layer or sand over gravel, the coarse grain layer here, we lay it down here. And then the one in front is those geobag containing the planting medium that we can plant vegetations in front of this. Okay, so and then after that we have a geogrid to strengthen the slope. So we have constructed at the 3 location. That is the schematic diagram. So what the one in front is the planting bag, and behind that is the fine grain, non-cohesive. That means we're using either sand or recycled material, and behind it we have coarse grain, non-cohesive, that is gravel or recycled material. Well, this is a site that we try. We have we demarcated it into 3 slopes, and slope 4 here is actually original slope, 35 degree. But we want to construct GBS in here, slope 1, 2, and 3, at an angle of 70 degree and height of 4 meters. And we're using the material that is recycled concrete, fine recycled concrete, or coarse recycled concrete, recycled asphalt, or combination of recycled concrete and recycled asphalt. And for slope 4 is the original slope. So that's the schematic diagram of the dimension. These are the recycled concrete aggregate, fine and coarse. And these are the recycled asphalt that we use. And these are the planting bag. You can see here the pocket. This is for the root bulb that we will insert it into this pocket, and then the root will grow into this bag. And inside this bag, it contains the approved soil mixture for planting. And behind it, there is a geogrid, right, for basically strengthening that structure. So this is during the construction, 4 meters, 70 degree. And this is the final product with all the plants in front. With that, we'll have a green wall. and it is sustainable development in urban area where we want to see greeneries even at the basement car park, and it's good. It will cool the ambient temperature, and it will give you a pleasing static view. And these are the type of plants that have been selected by the landscape architect because we want the plants that can grow and can survive under low light in the basement car park area. So, and then of course we need to monitor performance of this by having instrumentations, the tensiometers, and also the moisture sensors. These are the water table, the response in the same way, like for the rainfall, and yet for the crest and the toe, and maintained basically at the more or less the same elevation. In other words, the infiltration has been prevented going into the site, and negative water pressures behind the geobarrier system remains essentially constant under that rainfall characteristic. Here is the factor of safety variation for slope with the GBS, remain constant under this rainfall variation. Then for the original slope, yes, the factor of safety to start with is higher than GBS, because in here you're talking about a slope angle of 35. But for GBS, we're talking about 70-degree slope. But the factor of safety for the original slope fluctuated quite a bit due to the effect of the same rainfall condition. These are constructions, the permanent GBS near the basement car park. So that is the basement car park over here, and that is the GBS. Give you a green wall. This is part of the sustainability effort. So this can be used to create, for example, a recreation area and maintain the flora and fauna around here, because we have lots of vegetations around the UBS, or can be used as to lining up the rail track, so that we have a green view, and also along the highway. Or if you have embankment or polder, and the inner part of this, you can put a geobarrier system and then we can make use of this land, because it can be constructed at a steep angle and yet give a green wall for the surrounding residents. Now, just want to quickly go on into the tree stability. For the tree stability, here we think we are aware sometimes during rainfall, many of the trees will fall. Again, the way we look into this as structures, upper structures, where we have a tree trunk and a canopy and the root. So the anchoring of this root and soil, that will also provide the foundation for this tree. Of course, the climate effect on the tree stability is important. So this is the way we consider it, as the upper structures, and the lower structures, or the foundation is the root. Now, can we improve this soil that will be used to anchor the root? So in the past, we used this topsoil basically to keep the moisture and the nutrients for the tree growth. And can we mix it with the granite chip? Right? Or we can change it later on with the what do you call it, the recycled material. So this to give the strength, so they have a higher anchorage. So this is basically that we want to do a mixing between granite chips and topsoil. This is the grain size of the topsoil, and this is granite chips. So if I mix it 50-50 by weight, or 80-20, these are the grain size distribution. But now, can this mixture has the capability to retain moisture and also to retain the nutrients, of course, that come from the topsoil. So the way to see whether the soil can maintain, the mixture can maintain the moisture, we look at the salt water characteristic curve of the mixture. Of course, the highest capability comes from the topsoil. Granite chip is the lowest, but the 50-50 and 80-20 is not bad. Be able to maintain the moisture under different suction value or under the different dryness of the climate. So that offer a potential use of mixing between the granular material and the topsoil. So the strength, of course, the strength of the granite chips is highest, topsoil is the lowest, but the mixtures will be in between. In other words, there is an improvement on the strength of the soil. So we did the field study where we have 20 plots and we have different mixtures and planting as a planting medium. Then we grow the tree, the rain tree, and then for 3 years, and we measure the tree growth to see if there is any effect, negative effect of this mixture compared to the topsoil on the tree growth. Apparently, our study showed there is no effect. The tree will grow the same way as if that is planted in the topsoil. So in the end, we pull the tree, measure the load capacity that the tree can take, particularly under different mixtures. So these are the moment during the pull-out test. And once we pull the test, pull the root, uprooted the root, the moment before the trees are uprooted, then we clean the root and we map the root architecture. In other words, we need to measure the diameter and also the volume of the root for our analysis. It shows that actually, yes, the maximum pulling force increases as the root cross-sectional area increases. So in conclusion, basically my presentations highlight that the unsaturated soil mechanics is relevant for sustainable urban development. I have shown the application for the development of the slope susceptibility map, for the slope monitoring, and also for the slope repair in the event that the slope factor of safety is quite critical. And the other thing is the also a little bit on the tree stability when we consider the mixture between the granular material or recycled material and the topsoil or approved soil mixture for planting. So the theories and the property measurements and construction procedure for incorporating this unsaturated soil mechanics are readily available for routine geotechnical practice. So now is our time to apply this unsaturated soil mechanics in order to have more sustainable urban development. Thank you.
Okay, thank you very much, Professor Harianto, for your amazing and informative lectures. So I believe we all learned a lot from these lectures, especially regarding the unsaturated soil mechanics. So if I can summarize a little bit, a few points that I can highlight here is soil property contribute to the slope failure, not necessarily due to the rainfall. And then we talking about soil properties in terms of metric suction, including the SWCC and also 5B. And one great point here is a fine grained soil is very good as a capillary barrier compared to the coarse grained soil. And also one of the point here is a geo-barrier system using the recycled material. Also at the end of your presentation, you mentioned about the why the tree, the pull-out tree, something like that, the pull-out test for the tree. Okay, to kickstart question and answer session, maybe I begin one question from me first. Okay, Prof, is it okay, Prof?
Yeah, go ahead.
Okay, based on your own experience, Prof, other than soil properties and rainfall? Does the mature tree, I'm not talking about the grass, I'm not talking about the vegetation, I'm talking about the mature tree. Is it the mature tree, from your experience, contribute to the slope failure? The mature tree, is it they contribute to the slope failure? Maybe due to the development, they cut the tree and something like that.
Yes, if you cut the trees, and then after that you let the root left behind rotten, and as a result, that decayed root become a preferred channel for the water to infiltrate into the slope. As a result, that will increase the infiltration into the slope, and stability of the slope can be affected. So I think it's very important questions that the tree should be, as much as possible for our slope, that we have to maintain the stability of the trees. Because once we do deforestation, that's the beginning of the problem, right? Especially, again, we always do is that we cut the slope, then we remove the top part of the slope. And those top parts usually have a low permeability soil. We expose the inner part of the slope that is less weathered as a result of the higher permeability, and then it will accelerate the infiltrations into the slope. So the deforestation and also the cutting of the slope have to be done in a careful manner.
Okay, so for the all viewers from Malaysia, from Singapore, and around the world, you are welcome to post any relevant question here. So maybe I will read later to Prof. Harianto during this session. Okay, so you are welcome to post any question in the comment, in the Facebook comment. Okay, maybe I give another question here. Prof, when you're talking about the capillary barrier, right? You using the fine grain soil. So what is the optimum depth? I mean the minimum one. So to ensure to protect the slope from fail or something like that. So what is the optimum? Okay.
The key thing is we have the coarse grain layer, the gravel layer, because that's the one that will provide the barrier. However, it doesn't have to be too thick for that particular layer. Now, the fine grain layer or sand layer, the thickness of that sand layer is a function of the rainfall amount on that local area. For example, in certain area, you have a very high rainfall. Right? So all this rainfall will have to enter the fine grain layer or the sand layer. So that sand layer should have enough capacity to absorb all this infiltration and then drain it as fast as possible. That is why we advise not to use cohesive material, because cohesive material, yes, it can absorb this rainfall, but it will not let it go. But if we have a sandy material, it will absorb this amount of rainfall, and after that, it will drain it out quickly.
Okay. Still don't have. Maybe there's a lot of questions outside there. Maybe they're going to hold the question first. Maybe they're going to contact you later.
Yeah. Sure, no problem.
So maybe one. Is it got one question? Okay. One question from me again, Prof. When you mentioned about you have a zoning mapping zone where you got a factor safety 1.5, above 1.5, and so below 1.5. So the zone that where you have a factor safety below 1.5. So what maybe what the government of Singapore doing for this kind of slope? Is it maybe they do the stabilization or something? We just ignore it or just leave it, something like that?
Certainly, we will not ignore it. So the slope that is having factor safety less than 1.5 we'll have to check. So we need to check the locations the proximity to the infrastructures, and then if it is maybe the factor safety 1.4 and so on, then we will monitor the slope if it is really in the risky area. However, when the slope have factor safety marginal, maybe 1.2, is too close to 1, then we need to improve it. So one of the methods is to use the capillary barrier system or other improvement with respect to the drainage system on the slope.
Okay, this is a question from Nur Jaslina.
Yeah.
So how to introduce unsaturated soil in engineering practice? Okay, Prof. Maybe just 1 minute.
It's a good question. I think that it is important that each one of us realize the importance of this unsaturated soil mechanics in understanding the real soil, because in the field we don't see the water oozing out on the slope all over the place. Slope is not fully saturated, but it's unsaturated. How do we apply in practice respect to the design and everything? We need to slowly introduce to the local practice. Of course, we need to show the reliability. So, for example, if we have enough measurements of suctions on that slope, then we'll be able to design the factor safety of that slope with respect to the suction that we have monitored for a period of time.
Okay, so I believe they got another question from Ishaq. Okay, okay, Dr. Fakrul Razi. Okay, okay. Further explanation, does any research regarding root after cutting will increase infiltration? There's any research, maybe this from Dr. Fakrul from UMP, University Malaysia Pahang, I believe.
Okay. Yes, I think there is some research, I can't remember which paper, that indicate as long as the root that you cut is healthy, it's still intact, it's no problem. But once start to decay, and then that becomes holes in the slope, and that water will penetrate we enter this hole, and then as a result, you will increase the infiltration. Yes, there are some research on this.
So I can, okay, you got another question. Is it okay, Prof?
Yes, no problem.
From Jawid Roshan. Dear
Yeah.
Prof, since we normally consider the saturated soil mechanics in earth structure design, we take into account the bed situation. Is it like, the question is not complete.
Yeah.
So maybe they mentioned about saturated soil and compared to unsaturated, something like that, if I understand the question.
Yeah. I think it is quite common to have design based on the worst scenario, fully saturated, right? However, in some areas have been found that actually the soil never gets saturated most of the time. For example, I think in South Australia, they even put it in a code of practice for the retaining structures that has, because they experience that many of the soils are unsaturated. So it is unnecessary to design to the extreme fully saturated. So therefore, it is better that we have more realistic design incorporating the unsaturated soil mechanics. So again, all these things we need to explore, but the theory is there, and then the measurements and the applications that we need to try.
Okay, so thank you, Prof. So I think due to the limited time, I think it's okay. Yeah. Maybe if you got any other question, you can just simply can email Prof. Harianto later. I believe Prof. Harianto more than happy to answer all the questions. Okay, Prof. Thank you very much.
Thank you. My pleasure. Okay.
It's really grateful and honored for me to have you here in this series today.
Thank you.
So I believe we learned a lot today. Thank you again, Prof. Now I'll give back to Prof. Rafiq for closing remarks. Over to you, Prof. Rafiq.
Thank you, Nazri. And to Prof. Harianto Rahardjo, our deepest gratitude to you for sharing your knowledge with all of us today. Thank you for accepting our invitation, and thank you for sharing your work on sustainable urban development. We hope that our collaboration will continue well into the future. And to all of you watching this program, and we have hundreds of viewers this afternoon from all over the country as well as all around the world. To all of you, thank you for watching this program. Don't forget to like our Facebook, because we have many more interesting lectures for you. Do share this video to all your friends and colleagues worldwide. Thank you for watching. I'll see all of you in our next episode of UTM Engineering Distinguished Lecture Series. Bye for now.
Thank you. Bye-bye.